Its implications on system performance and design, reliability, and life cycle cost of the monorail system can be pretty considerable. So with that, let's talk about monorails. And no, actually not these monorails, more like this one, Newark Airport, or the Dusseldorf H-Bahn, the Siemens system, or Sao Paulo Line 15. Or even going back to the Wuppertal-Schwebebahn, I think built around 1901. So since their early beginnings, monorails have been largely powered with a system of electrified bars made of various materials commonly referred to as power rails. And while the concept of power rails is fairly straightforward, there are several design considerations critical to making these systems efficient and reliable. So let's start with a brief look at the subassemblies which make up a power rail system. So power rail systems typically consist of these 9 basic components. Conductors, which conduct the electricity and provide a contact surface, sliding contact surface from which the vehicle pulls power. Splice assemblies, which join those conductors. Insulated hangers, which both insulate the conductors from the guide beam and support them, attach them to the guide beam. Expansion assemblies, which manage the thermal movement or expansion of the conductors. Anchors, which help control and direct that thermal expansion. The power feeds are simply just the feed connection, cable connection to the power rails from the substation or traction system. Transfer caps or ramps, which help manage the collector through gaps and switches. Power isolations, which segment the power rail into zones or blocks. And then the collector assembly, which is essentially the interface between the vehicle and the power rail, provides a sliding contact for transferring the power to the vehicle. So the conductor rail is, while the most prevalent and cost-effective configuration for modern power rails is extruded aluminum conductors with stainless steel contact surface. The aluminum provides a sufficiently low resistance, about 55% the conductivity of copper by volume, with excellent strength and stiffness, lightweight, and good corrosion resistance. The stainless steel contact surface protects the aluminum from mechanical wear of the collector shoe and provides improved resistance to electrical arcing. Now, this combination of materials really provides a durable, cost-effective, and electrically efficient conductor of sufficient mechanical strength and stiffness. And the conductors can be easily cut to length and curved as needed for installation. The relatively low cost of aluminum extrusion dies really makes this easily adaptable and cost-effective material to produce in fairly low volumes in a wide variety of profiles and configurations. The conductors are shaped for use with either a guided collector, typically smaller systems in AC, kind of like the center one here, the 1500 amp, or a pedal-type collector shoes for higher current capacity and typically DC applications. Conductors can range in length from 5 to 15 meters, with the length ideally being a multiple of the support spacing, so that the splice joints don't interfere with the hangers. And conductors can be covered or bare depending on the guideway design, environmental considerations, and size of the conductors. The insulating cover materials are typically extruded plastics such as PVC or polycarbonate ABS alloys. And of course, for outdoor use, those need to be UV resistant. And for indoor use, should be low smoke and toxicity. So the splice assembly is essentially a mechanical and electrical connection which must equal the strength and conductivity of the conductor. And these may be through-bolted, as we show on the right-hand side. You see the 2 conductors that are drilled through or punched with splice plates and then through-bolted. On the left-hand side, we have, which is essentially a friction splice. So this profile conductor is shaped to accommodate the head of the splice bolts. They slide in, fit in these slots, and the splice plate is joined. And essentially, this is a friction splice. But actually with quite a high holding strength and fairly low resistance. So the insulated hangers, now these bolts support and insulate the conductors from earth and the other poles or phases, while allowing thermal expansion of the conductors over the whole temperature range. So critical considerations for the insulated hangers include mechanical strength, dielectric strength, the ability to withstand impact loads from short circuit events, and the allowance for thermal expansion of the conductors. So you want to securely hold the power rail, but not so tight that it can't slide, can't move under thermal expansion. Expansion assemblies, these take up the thermal expansion of the conductors while maintaining conductivity across that expansion gap and also providing a smooth, continuous contact surface for the collectors. Now, given that aluminum has about twice the coefficient of thermal expansion as steel, even just under ambient conditions, we'll expect that power rail to grow over temperature twice as much as the steel does. And then we add the additional heating due to current. Of course, that will move for, expand further. So expansion management is pretty important, particularly with aluminum conductors. So the design criteria include the electrical resistance through the assembly, minimal deflection of the assembly as the collector crosses that expansion assembly, and proper coordination of the geometry of that gap with the shoe, so the shoe doesn't fall into that gap and it guides it smoothly and quietly across that expansion. Anchors essentially serve to secure the conductors to the hanger at specified intervals. So think of these spaced in between each of the expansions midway. Another expansion spacing may be 80 to 200 meters depending on the temperature, the size of the conductor, the ambient and current heating. So these anchors may be either a friction clamp or through bolted design, but they must be able to withstand the force of the collectors under expansion and contraction as they counteract the force of the conductor sliding through the hangers. Next, the power feed. So really this is the point of connection for the feed cable to the conductors. It's advisable to position these at the anchors or position anchors at the feed points to limit the stress on the feed cables from that thermal expansion or movement. Otherwise, very finely stranded, DLO type feed cables should be used to accommodate the movement of the power rails relative to the guideway. So here on the left-hand side, this is Las Vegas monorail. This is set up with quite a bit of loop here, quite a bit of flexibility. And of course, Las Vegas, you've got some pretty wide temperature swings. So this is nicely configured to allow movement of the feed point. In the case of line 15 Sao Paulo with very large cables, these really serve essentially as anchor points, and the conductor bars are anchored in close proximity to the feed points. So transfer caps or ramps. This is where probably some of the more complex coordination, design coordination, and component configuration of all a power rail system. Because essentially what you're doing here is managing a collector across a switch gap. And the key here really is to ensure minimal collector movement and a smooth, quiet transition of the shoe across the gap. Now, one of the things about this is that when the collector is moving across this, it's making and breaking contact, or breaking and remaking contact with the conductor bars that crosses that. When this happens, you get some sparking, arcing. That arcing creates electrical erosion. So these typically are the areas of highest wear, and that's wear due to electrical erosion. Mechanical wear of the stainless steel conductors is very minimal compared to steel conductors or copper conductors, but the key here and the most important consideration is electrical erosion. So this make-break contact can result in higher than normal arcing, and one way to manage this is to have short sacrificial sections of conductor that can be easily replaced as these are electrically eroded. This is a slight cast bronze transfer cap down in the center lower photo, and then behind it you'll see there's a short, about a 1 meter length sacrificial section of conductor bar that can be easily replaced. Now, power isolations essentially electrically isolate the fed sections of the power rail into zones or blocks. So air gap, rather than a solid insulating section, really provides better isolation. And on the left-hand side up here, you'll see on this small, it's about 1,000 amp conductor, we have a Delrin spacer block with a step, and then an FRP pultruded, I believe that's probably a channel cross-section to provide stiffness and strength. But you'll notice this open air gap provides better tracking and a isolation, because over time these will accumulate with dirt, debris, moisture, collector dust, and become conductive. So there is a bit of maintenance to these, or there can be. On the right-hand side, this isolation configuration essentially consists just of FRP rods that are through-bolted to the conductors, and you'll see this angle of the cut or break in the isolation provides a pretty good gap, fairly long tracking distance, but still enables the collector shoe to transition it smoothly and at speed. Collector assemblies, this again is the bridge between the vehicle and the power rail. Their job is to maintain contact with and draw power from the conductor rail. The collector shoes are a consumable item, really the only consumable item in a power rail system typically. And they can be made of various materials, anything from cast iron to copper or copper graphite or some sintered metal. But the shoes need to have good wear properties and must maintain acceptable temperatures under steady state and transient current loads. And the collector must have sufficient range of motion to maintain contact with the conductors through the complete range of vehicle movement and loading. So putting all together, here's our typical section of power rail with the conductors of consistent length spliced together and supported at regular intervals with the insulated hangers. The anchors control or direct the expansion of the conductors toward the expansion assemblies, and the power feeds provide cable attachment points. And the isolation segments, of course, segment the power rail into zones of blocks, and transfer caps or ramps then manage the movement of the collectors at gaps and switch gaps. So there's just kind of a quick and dirty overview of what makes power rail system. Now that we kind of have a basic understanding of that, let's delve into what I consider to be the top 7 design considerations for monorail systems. And although there's a general priority of consideration in these 7 categories, their interdependencies really necessitate an iterative approach to system design and development. And you'll see these arrows that I've drawn here really just kind of indicate where there are interdependencies in these considerations. So it's not a one pass-through design and development, but typically something that requires several passes. So first, sizing and selection. Understanding the electrical requirements obviously is really key to proper power rail selection. Resistance and vehicle current are really the 2 most important specifications for preventing excessive voltage drop, essentially ensuring that you have adequate power throughout the system. Operating voltage also dictates insulation levels and allowable clearances. So obviously resistance drives voltage drop, current rating has an impact on the heat rise. The operating voltage, of course, drives consideration of insulation and clearances. Now, power rails are typically described in terms of their maximum steady state current, for example, 1200 amp conductor. But really for 99% or maybe even more of monorail systems, conductor resistance rather than the current rating really is the primary design criteria. So therefore, the most helpful specification to the power rail supplier is a resistance per unit length. So to illustrate, this graph kind of shows how a bit arbitrary the specification of current rating is. This is the heat rise test of a conductor, and you'll see that the temperature doesn't really stabilize until about 5 hours. So for this 4,500 amp conductor, it takes about 5 hours to saturate and reach stabilization. Well, probably isn't a system on Earth that is pulling that kind of RMS current. Again, it really is about voltage drop. But it's helpful to know what we can expect in terms of heating of the conductor for proper expansion management. So voltage drop from the feed to the vehicle is a function of resistance, of course, and is temperature adjustment, and of course the current demand. So this graph shows the voltage profile for a section of power rail. It's about 1,535 feet. My apologies for not using metric, but we're on the order of 500 meters here. With feed points, 2 feed points located at 528 feet and 1,100 some feet, under a steady current of 655 amps. So the blue line indicates our temperature-adjusted voltage at 0, and the green one is 110. And here you can see just how, with the 2 feed points, we've got a obviously much lower voltage drop than we do at the tailings on the ends. But this type of evaluation is helpful to know really what available power there will be along the system. So consequently, current rating of power rails is really a function of operating temperature, and therefore is always stated at a specified temperature rise at a given ambient temperature. So a given conductor will have different current ratings at different temperature rise and ambient temperatures. So for the conductor referenced in this graph, operating at an ambient temperature, for example, at 0 C with a maximum allowable operating temperature of 85, that would classify that as a 7,500 amp conductor with steady, state current capacity. But the same conductor at an ambient temperature of 40 C with a maximum temperature of 85 yields only about 6,500 amps of capacity. So there's a bit of an arbitrary nature to the rating, but when the current rating is specified in terms of temperature ranges, then now it's much more meaningful and precise. So optimization. There may be some opportunities where it's economically advantageous to use different conductors with different current requirements along the guideway. This large depot facility here in Sao Paulo, line 15, there's several kilometers actually of depot conductor. The section lengths aren't very long. The power requirements aren't very great. So given the amount of power rail that would be needed to feed this, it's logical to downsize the conductors in that area to save money. You could configure those conductors so that all the accessories, the hangers, the insulators, splice joints would all be the same, but you've essentially taken some material out. And again, with the cost of extrusion tooling, this type of modification isn't very expensive. So these areas offer opportunities for reduced power rail costs through smaller cross-sections. An example of such optimization, these two conductors were used for the Jacksonville monorail, the Skyway, Jacksonville Automated Skyway Express. It uses both a 700 amp conductor on the left and a 1050 amp conductor on the right. The 1050 amp conductor was used only crossing the Costa Bridge over the St. Johns River, where there was a steeper incline, the vehicle pulls more power, but for the rest of the system it uses a 700 amp. The splices, the insulating cover, the hangers, all the other accessories are all the same. And simply by adding a little bit more material in certain areas, we were able to provide higher capacity without having to upsize the power rail for the whole system. So voltages are typically 600, 750 volt DC or 480 volt AC, and that's, of course, those are the primary drivers for insulation design. Environmental conditions like UV exposure, moisture, pollution levels also have a significant impact on the effectiveness of those insulating materials and should be considered in system design. Insulators must be designed with the necessary geometry and materials to meet system requirements. And those essentially are mechanical strength, both under normal conditions, we would say, also fault conditions if there are some expected, as well as providing the adequate creep distance in the specific environment. And that creep distance essentially is this black line, the distance from the conductor, the live conductor, to grounded surface. Lastly, increased voltages have diminished benefit for all but really the largest monorail systems. And although power losses, I squared R losses decrease as voltage increases, thicker insulation, the greater electrical clearances, and the likelihood and consequences of stray currents associated with higher voltages typically offset the power savings advantages of operating at higher voltages. So we just don't typically see monorails, or maybe a few at 1.5 kV larger systems, but generally they're in the 700 volt DC nominal range. So the power rail's purpose is really to supply the needed power, obviously, voltage times current, to meet vehicle demand. So the demand is based on a design specification of passenger movement, so many vehicles at certain headways, and obviously it's essential that that power is always available to meet the design specifications for that system. So there are a couple of ways to achieve this. Spacing the feed points for incoming power, those need to be spaced at optimal intervals at the system to provide adequate voltage. Certainly it's important to achieve a balance between the number of feed points and the size of the power rail. And this is where you want to call on your power rail supplier maybe to say, listen, here are a range of options. And it's not unusual to quote early stages, say 500, 700, and 1,000 amp conductor, to see how it's possible to optimize based on the size of the conductors, the size and the spacing of the feed points or substations, and come up with the optimal design. So the power distribution considerations really boil down to meeting power requirements in the most economical manner. And that's considering all aspects of the life cycle cost, not just first cost. So this current demand graph from this load flow analysis shows current, RMS current, as a function of location along a system. The vertical peaks indicate the location of the substation feeders, and the negative spikes, which typically are right next to those because these substations are located at passenger stations on this system, are low because of the dwell times when the vehicles are stopped. So the way this is essentially designed is it shows that this vehicle, as it first accelerates leaving from this station, the current is fairly high and the RMS current is high because this feeder is feeding this section of bar until it reaches a crossover point at isolation. And that current demand, of course, decreases from an RMS level as the vehicle passes. So the RMS current levels are highest, obviously, closest to the feeders. They drop off as you move away. So this is normal operations. Now, it's likewise important to consider the failure modes of the power distribution system, specifically what happens if you lose a substation. So in this case, both the RMS current and the voltage drop may increase significantly. So this is a graph from the same system, but essentially what they're assuming is that from 0 to 2 kilometers in this between the first two stations, that in this case we've lost the second substation. In this case, we've lost the first substation, and this doesn't represent a realistic continuous, but it shows you what could be expected in terms of current demand if the substations on either side go down. So here, of course, now your RMS current levels go up considerably. So to mitigate the effects of substation loss, you have to decide whether you want to accept decreased capacity or increase the number of substations and or increase the capacity of the power rail. In this case, the customer decided to increase the capacity of the power rail to decrease the voltage drop to improve the power performance in case of loss of a substation. So such trade-offs are pretty common in power rail design, and substation location is influenced by a host of factors other than power rail as well. It's not always easy to locate those maybe between stations. Stations are a logical place to place those. So also considering grid connections, space in a built-up environment, and geography will also drive the flexibility of locating substations. So for dual lane systems, it may be preferable to position the ground return conductors on the inside of the guideway, such as was done on line 15 in Sao Paulo. Now, this simplifies cross-bonding of the returns, but can complicate the collector configuration on the vehicles for a pinch loop system. Essentially what you need then is the vehicle transitions to the point of crossover you're going to have double sets of collectors as the collectors pick up the alternated conductors. And it also requires the reversal of power phases in the power rail. That's essentially what we're showing down here. So in this switch assembly, this crossover switch, where we would have a tangent condition, as we go into crossover mode, we have to incorporate this phase reversal element in the conductors to switch the phasing. The effects of short circuit loads are also well, typically not a big concern for DC systems on monorails because the positive and negative conductors are on opposite sides of the beam. The spacing generally reduces those forces to certainly well within the capacity of the hangers and the splice in the conductor bar. Now for AC systems, the conductors may be on as little as 3-inch or 75, 80 millimeter centers. So it may be, fault condition may be important, so it's important to take a look at what the resultant loads will be on the conductors, adjacent AC conductors in a fault condition. And sometimes that can be proven through calculation. In other cases, it may be necessary to conduct some testing of the components to verify that they'll withstand those short circuit loads. So guideways. Typically, these are beams of concrete or steel mounted or suspended from the columns. The coordination with the guideway really is every bit as important as the electrical considerations in the design. Attachment of the power rail supports the guideway geometry, thermal expansion, electrical clearances, positioning and routing of feeder cables are really best addressed early in the system. So when what's the best way to orient the conductors? Well, what are you trying to do? What do you need for power? What's the vehicle configuration? Ideally, the earlier in the design, again, that these things are discussed, the better. Generally speaking, the orientation is the size, a function of the size and the number of the power rails, the beam design, and of course the vehicle design. It's pretty simplistic, but it's the details that really make a difference in terms of ensuring a cost-effective, reliable system. So for larger power rails, the orientation is typically some side contact configuration with the power rail contact surface aligned to the vertical, as you saw in those photos for line 15 in Sao Paulo. For smaller shoe-guided conductor profiles, such as what we have over here on the right-hand side, a bottom orientation is usually preferred because this keeps the contact surfaces from being exposed to the weather. The collector shoes will deposit a lubricating graphite. If you have a lot of rain, that graphite can be washed away periodically. It causes some issues with shoe wear. However, in the case of like H-bond, an enclosed beam, orienting those in that configuration would certainly not be a problem. So secure and precise attachment of the power rails to the guideway really is essential for reliability as well as power rail longevity. Maintaining proper position of the rails relative to the collectors ensures that the contact force, contact area, electrical transfer efficiency really remain within acceptable limits through the life of the system. And typically power specifications include a maximum allowable deflection in the event of damage to or loss of an insulated support. What I'm trying to say here is that the system should be designed, the supports of the conductor should be designed such that you can have a hanger, maybe lose a hanger or something breaks, the system will still operate, the conductors will still be within tolerance of position to allow the system to, the vehicles to move. So adequate electrical clearances, of course, also must be considered between the vehicle, the power rails, and the guideway. Let's see here. There we go. Beam surface condition. Well, any loss of any condition which creates a loss or intermittent contact with a collector shoe with a power rail, bouncing of the collector creates arcs. Arcs create electrical erosion to the contact surface of the conductor, and this is damaging to it. So when the electrical erosion occurs repeatedly in a certain section, it kind of creates a cheese grater effect, and this hard, sharp contact surface can then severely damage shoe life. So if not detected in time, the combination of a severely worn shoe and a conductor surface that's pitted, that leads to this downward spiral of condition and requires essentially replacement of the conductors. So it's important that the guide beam surface is sufficiently smooth. Obviously it needs to have to ensure tire adhesion for acceleration and deceleration. However, when beam roughness is excessive and produces a rough ride, collector shoe contact with the power rail can be compromised. And this produces arcs and sparking and can lead to premature failure of the power rail contact surface. Guideway switches, another kind of complicated area. They really come in three general configurations: sliding beam, rotating beam, and articulating beam. And each type imposes some requirements and limitations on the power rail system, which would include collector shoe length, vehicle speed, switch point geometries, and conductor orientation must really be taken into consideration to ensure a good system. So it's critical that the minimum electrical clearances are maintained through the full range of switch movement, because it's not uncommon to have live conductors passing by grounded elements or opposing polarity conductors. I've got a little video here. I'll show you animation of a sliding beam switch that we put together for our customers. We were really figuring out how we were going to position these conductor bars to ensure clearances. So here you see the sliding beam, the conductors. This is a plan view. The conductors are on either side of the beams. It'll switch here to end view. So we're on the free end, and here you can see these conductor elements. And those conductor elements are passing fairly closely to the beams as well as to the opposing conductors. I think the next view here we'll see the fixed end of the switch. So here you can see where clearances again come into play. We want to minimize the gap across those transfer caps, of course, for smooth shoe, quiet shoe operation, shoe longevity, but we also need to have clearance. This zoom in shows the phase reversal that I talked about earlier. This system has the ground conductors inward facing on the guide beams, so it's necessary to reverse the phase of the collectors at the crossovers. So as the guideway curves, well, obviously so must the power rail. And as a general guideline, power rails must be pre-curved for radius about below 100 meters for conductors over 1,500 amps. Smaller conductors, probably you need to start pre-curving those at about 30 meters or less. But interestingly enough, aluminum conductors are fairly flexible and can withstand a fair amount of in-situ flexing without placing undue stresses on the insulators, the hangers, or the guide beam. Thermal expansion is a big one, big consideration here, both in terms of the absolute ambient temperatures and current heating of the conductors, as well as the relative movement of the conductors to the guideway. The poor expansion management can lead to all kinds of problems. Conductor snaking, breaking hangers, can sometimes be so severe that the collectors are unable to maintain contact with the power rail. So it's really important that the guideway expansion joint movement is considered along with the conductor thermal movement when designing this. Now sometimes, many times, that guideway expansion detail, quantity, stroke, and location is not available at the time of the power rail system quotation. And this can lead to either an unreliable system, inadequate expansion management, or a bill of material and system price changes later in the project. So where possible, it's best to coordinate this as early as possible with the guideway expansion joints. This greatly simplifies the interaction between the two elements and ensures a safe, reliable power rail system. Proper positioning of power rail Key points, I mentioned this earlier, cable attachments, pretty important. Make sure there's flex. If not, make sure you're anchoring the power rail at those cable attachment points. Environmental conditions, these can vary widely, but primarily temperature, of course, in terms of thermal management, precipitation, moisture for insulation, sunlight, the effects of UV on the materials, sometimes even wind for covered systems. For example, systems that are in hurricane zones. We have a criteria where the covers must stay on at 160 miles an hour. So I'm not sure what you do about the trees and the automobiles that are flying, but at least the covers will stay on the power rails. So sand, dust, and corrosion, those are also concerns as well in a variety of whether a seaside or a desert environment. So a fair amount of things there to keep in mind. So in areas of high solar radiation, again, I mentioned UV resistance for materials is pretty important. And here on the left-hand side, you can see kind of some before and after of unprotected, really non-UV resistant insulators and the deleterious effect of UV on it. Precipitation can be problematic, whether it's rain or snow. Obviously, in very cold environments, it's possible that you may get ice formation on the conductors. Ice is not conductive, so the vehicles won't move. Or if it's intermittent ice, what you'll get is arcing and sparking as those collectors are making and breaking contact across the ice patches, and that could be damaging to the conductors as well. So, in fact, 1 APM in a tropical environment with a lateral contact exposure suffers very, very high shoe wear every time it rains. And it takes a while for that graphite to be redeposited on the rails and the shoe wear goes back to normal. So where possible for open conductor systems, a bottom running or bottom contact orientation significantly reduces the effects of precipitation. In cold climates, the center here, heater wire systems can be an effective way to prevent the formation of frost and ice, but they're not intended as a thawing system. The idea here is that these are to be turned on before the environment reaches freezing temperatures to prevent the formation of ice. It takes a considerable amount of power to de-ice, particularly these conductor systems with such a high ratio of surface to cross-sectional area. I mentioned lateral orientation, kind of hard to see. This is Jacksonville Monorail, but the conductors are this is AC system, side-mounted, and these are essentially exposed to the weather, and every time it rains, the shoe wear definitely goes up. Vehicles. Now, under normal conditions, the interaction between the vehicles and the power rails is confined to the collector assemblies. Accurate and detailed analysis really needs to be conducted to ensure that the coordination between the vehicle and the collector movement and the position of the power rail, the guide beam, that contact is maintained. And this needs to be considered really over the whole range, the dynamic range of movement of the vehicle in all load conditions. So, imagine a flat tire on one side with high crosswinds and sumo wrestlers sitting on one side of the vehicle. You're going to have a very extreme loading condition, maybe a decreased contact between the collector and the power rail. So these need to be understood and considered and anticipated in the design. So here you see as installed. This was the Bombardier Inovia 300 monorail with the phase reversal, the double collector arrangement. Installation. Well, without proper installation, the most well-designed power rail system is bound to fail and perform as required. So correct and cost-effective installation really starts with the detailed alignment drawings showing position, location of all the power rail elements. A complete and detailed installation manual is also a necessary reference for assembly configuration, procedures, specifications. And where possible, alignment fixtures or jigs should be used to facilitate accurate and precise positioning of power rail components on the guideway. So here you can see an example of a manual showing the joining of a splice plate, tightening specifications, orientation of all the hardware. On the right-hand side was a fixture used to properly position both the positive and the negative hangers in the guide beam embeds to support the insulated hangers for line 15. Oh, what's missing? What's missing here? Well, I won't name the system, but here we have a hanger. This is about a 3-meter pitch, and we get to here, and there's no hanger. Oh, there's a splice there. So they didn't put a hanger in. So here, the splice interfered with the hanger, and they decided not to put it in. Well, while it seems like a gross omission, as I mentioned earlier, the effect of this will probably be pretty minimal because the system, the design specification, often include a maximum allowed power rail deflection where a hanger is missing or damaged. So not ideal. Sometimes it's not easy to relocate those hangers. Ideally, what they could have done was cut the power rail and drilled it to relocate that. Sorry, I jumped ahead to the next slide here. But anyway, so packing of materials, bulk or kitted. A lot of times it kind of depends on how the material is going to be positioned on the guideway, moved, cost of labor, available storage. But arrangement and packing of the materials really does play a critical role in project success. You know, when these components are produced, they're handled. So when we handle them in the factory, it's the ideal time to then, if they need to be organized or sorted or kitted, that's really the best time to do that. The cost to do that is lower in the factory than it is out in the field. So we strongly advise that there be some discussion about how the power rail components are being packaged and kitted and identified. Storage is pretty important too. Obviously, that can have some severe effects. I don't think that the conductors were taken to the plastic limit, probably not damaged in this case, but there's potential for damage when crates aren't properly handled and stored. Let's get to maintenance. The biggest items really are collector shoes and then the effects of electrical erosion on the contact surface. So generally speaking, these systems don't require much maintenance. But periodic inspection of the system and its components is really important to ensuring long, trouble-free life and kind of understanding what your maintenance intervals will be, whether it's for cleaning isolations, detecting and replacing areas of high electrical erosion. This is actually a light rail system, but this is an engagement ramp. You can see the collectors are hitting here, making contact. You can see the effects of the arcing and the sparking. And as that collector bounces and slides along until it settles down, it continues to electrically erode that power rail. Not an ideal ramp configuration. That's actually pretty crude, which is part of the problem, the root cause of that. But the collector shoes really are the primary consumables in the system and are really the critical link between the vehicle and the rail, of course. So during initial system break-in, the shoe wear will typically be relatively high as small discontinuities in the power rail contact surface are filled with shoe material. And then usually within 1 or 2 sets of shoe, the shoe life will increase and stabilize. And this shoe life, it ranges from a few thousand to several tens of thousands of kilometers of travel, really depending on a lot of factors. And these factors include the number of gaps, switches, number of expansion assemblies, as I mentioned, exposure of the contact surface to precipitation, which will remove some of the lubrication, the speed of the vehicle, the guideway smoothness and geometry, even the collector shoe dimensions and collector design, and also the vehicle dynamics. So a lot of moving parts here. The quality of the power rail installation, particularly preparation of field cuts, is really important. When you saw cut through an aluminum stainless conductor, you will have burrs. If you do not remove the burrs of the stainless steel contact surface, the shoe life will be significantly reduced, and on the order of factors of 10 or to 50 even. So very, very important wherever field cuts of conductors are made that the conductor surfaces are properly dressed or deburred, prepared to ensure a smooth contact surface for the collectors. So when the shoes do wear beyond their service life, then you're going to have decreased contact area with the conductor. This increases the current density, And this current density, again, also can increase the rate of pitting and electrical erosion of the stainless steel contact surface. Again, this downward spiral of performance that I talked about can be a real problem if left unchecked, and the only solution then is to replace those sections of power rail that are damaged. So it's really important then to conduct daily checks of shoe wear starting from commissioning through the first several months of operation until it's stable and predictable. You know, thorough pre-commissioning inspection is really an effective way to maximize the life of a power rail system. And by identifying potential issues, whether related to installation design or specification, pre-commissioning inspection reduces risk to both the customer, the power rail supplier, even the contractor, the installer. And state-of-the-art data acquisition systems can provide an accurate and thorough evaluation of the power rail system by recording critical performance data such as individual and total vehicle, individual collector and total vehicle current, which is we have down here on the right-hand side. Collector impact and bounce, which we show here up on the upper left. Voltage measurements along the system, as well as monitoring voltage at the substations. And by GPS mapping these with the data acquisition system, we can provide a good mapping of the condition of the power rail system, identify punch list items for the contractor, and then provide them certification that the installation is done to standard, to specifications, and provide assurance to the customer that the system is then accepted and commissioned. And this also serves as a baseline then for subsequent measurement as the system ages to look to find hot spots, areas maybe where things have gotten out of gauge and collectors are bouncing and arcing. Use of both infrared and visual spectrum video can also be helpful as well to identify problem areas. So the state of sensor technology has significantly improved, and the price points have decreased to where this type of technology is really quite cost effective and helpful. So this shows some simultaneous data capture from our, we call it Prius, Power Rail Intelligent Analysis System. So we're tracking vehicle speed, we can see the current demand, we can see voltage, how voltage is varying, and then we can also see the collector bounce. And sometimes these may be co-located, one problem may cause another. Obviously, when current increases, we expect the voltage drop. So not all of the voltage events, though, in this system were correlated with the collector impact. So by simultaneously recording the substation power conditions, current and voltage, and time syncing that with the vehicle, we can determine what voltage variation is due to the guideway or the power rail, is how much of that is varying with the current demand of the vehicle, but then also identify if maybe there are some power supply issues, maybe with the substation or the grid connection that may be resulting in this as well. So it's important, again, to look at this as an overall system and not just the power rail. And then typically what we'll do is identify these specific locations of concern, go out with the customer, help them correlate the data with a physical characteristic on the guideway and understand how these conditions manifest themselves. So, as I mentioned, power rail design really is an iterative approach, requires identification and understanding and evaluation of several trade-offs. You know, it's not really so critical where you start, you know, as the chicken or the egg, but that you consider all necessary aspects of the monorail system when designing the power rail system. So in summary, I guess these are my kind of 5 key points here. So the more detailed and complete the power rail specification prior to final request for quotation, the greater likelihood of a firm price with on-time delivery. 2, iterative design process yields the best results. So optimal designs are based on understanding and prioritization of the numerous trade-offs. The further along the system design, the more disruptive to schedule and budget will be any changes. I guess that's a truth for really any project. Also be certain that the power rail is installed to the manufacturer's specifications. Include installation training and commissioning inspection in your scope of supply to make the power rail supplier a partner in your success. use their expertise to help you manage your project risk. And then lastly, perform proper routine maintenance. Too often we see that the O&M manuals that we spend a lot of time and effort on are not read, not followed. They may be lost. Ask for hard copies, get digital copies, distribute these throughout the organization. And also include training for the maintenance staff in the project scope of work. Many times as a supplier, we're actively involved with the contractor. We provide training, installation training, and commissioning support, but then it's handed off to the customer, and that contact isn't always maintained. So it's where possible, reach out to the original Power Rail supplier and involve them in the life cycle management of your Power Rail system. So I think, as anybody knows, we think about success as a straight line, but the reality of it is it's a winding and sometimes longer path than we prefer. With that, we'll open it up to questions. Recommended gap between Power Rails, and I'm assuming you mean two Power Rails on the same polarity. So it really depends on the collector shoe. A good rule of thumb is that if the collector shoe, as these typically are, is articulated, and that is that it has imagine a shoe that has a post supporting it, and that collector shoe can rotate on the end of that post, that the gap in a collector shoe obviously can't be any longer than half the length of the shoe. Otherwise, that collector shoe will tip into the gap. So, in fact, that's why ideally collector gaps are at a bias. Generally speaking, though, let's say a shoe that is let's say 150 millimeters, then we want our gaps to be less than 75, probably closer to a third of the length of the shoe. So for a 150 millimeter length shoe, it's ideal to have the gap somewhere in the order of 50 millimeters. But these are kind of general rules of thumb. As far as spacing between phases, question regarding the current versus chainage graph, difference between the red and blue lines. Let's go back to that. Oh, red and blue lines. Yeah, okay. This was the, I believe this was, yeah, I think this is what we're talking about here. These were actually at two different RMS current values. And I think this had to do with vehicle loading and train configuration. I'm not exactly certain, but I do know that these two conditions were based on vehicle configuration. So I hope I've answered your question. That's a good question. Pickup guides. Yeah, anytime you're making a transition there, it can be a bit difficult. Well, I can tell you that for smaller V-contact surface conductors, we have managed collectors through switches. Now, these are switches where you've got 20, 30 millimeters maximum of gap up to 100 kilometers per hour. But a pickup guide, really where you're disengaging and re-engaging the collector, we've done some, third rail systems. Typically, these are, approaching, speeds of 60, 70 kilometers per hour. It really kind of depends on the size of the conductor, the amount of space, the room that you have. Obviously, the ideal pickup guide would be a very long, gradual transition of geometry to gradually pick that up, but establish good firm contact so we don't have too much electrical erosion. So I'd have to kind of get into specifics in terms of what size power rail, what the system configuration is. But general rule of thumb, I know on LRT systems, these have been up to 50, 60, 70 kilometers per hour. You will get some electrical erosion because of arcing, as you saw in the photo, but I'd say that's probably pretty safe. So the question is, what's the minimum clearance between the surface of the guideway beam versus the external surface of the power rail, the concrete, minimum clearance? In this case, it kind of depends on how your insulators are configured. It's possible, for example, with a bottom contact conductor, to have that conductor very, very close to the concrete beam. So now really the consideration is through the air clearance rather than over the surface, because if we have the insulator kind of above the conductor, we can have a lot of insulator creep distance to support that conductor, but have the conductor fairly close to the guide beam. Now that would be for a bottom contact. For side contact, it gets a little bit more difficult, a little bit more complicated. So depends on the orientation of the conductor and the size of the conductor, but generally speaking, minimum clearance. Now in the U.S., the code says 3/8 over the surface, 1/2 inch through the air for at 600 volts. So we would need 12.5, 13 millimeters of clearance to meet code. Now realistically, given tolerances, construction tolerances of 6 and 8 millimeters, I would say that's not adequate. So you have a couple of things here that you would need to look at to determine that. But I would say a safe rule of thumb, I would want that, at least 50 millimeters away from the concrete. What about the gaps and expansion joints? Did we follow the recommendations that you said earlier? The gaps. The gaps and expansion joints, one thing I didn't mention is during installation, these need to be set based on temperature. So we take the ambient temperature of the conductor, we go to a gap chart that's based on the total range of expected movement of this, and that expansion gap is set. So do we follow the recommendations I said earlier? I'm not exactly sure. Now my recommendation is that you put those expansion joints and co-locate them with the guideway expansions. We'll have cases where we'll lay out the conductor bar and we identify, well, optimal spacing for expansion assemblies. And interestingly enough, the expansion assemblies are fairly expensive. They're relatively more expensive on a factor of 2 or 3 than a section of conductor bar. So we want to use those very efficiently and minimally as possible to keep system costs down. So if I look at it, just the conductors attached to a concrete beam, maybe we can go with 130 meters. But if we find out that the guideway expansions are at, let's say, 100 meters, well, now I need to decrease that. Can we supply the system in stainless steel 316? Yes, 316 is available. We have one customer in particular for some applications, Seaside, who specifies a 316 stainless. So yes, that's available. How do we manage several power stations on one rail? Do you separate the system into several isolated sections? And essentially what we're talking about here, are these bridgeable or non-bridgeable, and are they connected? Now typically they are isolated, but they're bridged, which means there's an isolation, but as the vehicle is crossing it, it's going to bridge those, but under normal operation, they're not bridged. In some cases, the specification is that they are not bridgeable, so you're going to have a vehicle typically cross through a switched section that can be disconnected that would require a transfer switch. So do you separate the system into several isolated sections? This is really a power distribution question, and it really depends on the scheme and how these substations are going to react to, feeding toward each other and what the implications are. How long does it take to get the system stable after commissioning? How long does it take to get the system stable? Okay, stable from a collector wear standpoint, it kind of depends on how the wear is. As I mentioned, it may be from a few hundred, several thousand kilometers. That's per a vehicle operation or shoe operation. So it depends on how many vehicles you have operating on the system, number of collectors, the headway. So essentially it comes down to number of shoe passes per day or month or week. So concrete beam clearance. So we're talking about a top-down contact collector. Okay, so we've got again, I would still go back to two considerations. One, you have construction tolerance of the guide beam. Also, there may be, depending on the size of the conductor, a little bit of snaking as that's expanding and contracting, so it's not going to stay perfectly in alignment. It may move, 4 millimeters, either side. Again, I would probably stick with something in the order of 25 to 50 millimeters at least. I'd be a bit afraid at 25, 50 would be better. So recommended maintenance period. Well, for collector shoes, that really kind of depends. It's kind of like they say with your tires on your car. Actual mileage may vary, so it depends on the nature of the system. I would be, initially with a new system, I'd probably be checking it every couple of weeks initially until things settle down. But again, looking at typically the key problem areas. Check the anchors, make sure they're holding. Check expansion gaps at various times to make sure that those are moving, if they were set properly initially, that you won't run out of stroke of those. Look at the areas where the collectors are making and breaking contact with the power rail to look for electrical erosion. And then again, look at the condition of the collector shoes. Sometimes those will tell you, based on nicking or chipping of the leading edges, that there may be some impact going on out on the system. So I guess that's it. Are there any other questions? And again, I think you saw my email address. I can bring that back up again. Feel free to contact me with any other questions or any other information. I'll slide ahead here to the last slide. Optimal distance between isolators. Are there standards to follow? Really, this is a, primarily it's a mechanical consideration. When you're talking about isolators, I think you're talking about the insulators, the supports. So we've got a couple considerations here. The primary one really is that the conductor stays in position. There's not too much flexing. And I could give you some examples of standards based on conductor size or specifications that we've been provided in the past you could use as a, as a reference. Again, that also depends on the collector, its range of motion, and its ability to withstand, that flexing of the conductor. Also, okay, so there's an installation with conductor bars in Philadelphia Airport. Conductors conduct, guess what's intensity conductor bars? Philadelphia Airport. I am not familiar with that, and that may precede me. I know there's someone listening who would know. That'd be Richard Prell, but I don't think Richard can, unless he can type in a response, but I'm not aware of that. So what is the intensity? Do you advise the rails to be positioned the same distance with respect to the guideway surface, or is it advisable to have them moving up and down? This is a very good question. It depends on the collector configuration. Excellent question, and I really appreciate it because I failed to mention this. But remember, the collector shoe that I showed was worn very significantly in one location. If you're familiar with overhead systems with pantograph collectors for overhead lines for transit, as you sit in the train and you watch that overhead line, you'll see that it moves, and this is to provide good even wear. So, for example, in Las Vegas monorail, where you have a fairly wide collector shoe, in fact, the collector shoe that I showed with that deep groove, they vary the position of that conductor, snake that conductor to get good even wear, and it gives you much greater shoe life. So yes, it's advisable. Variation of movement, general rule is within 2/3 of the total length of the shoe. Part of it depends on the loading conditions. So we need to make sure that over the whole range of loading conditions of the vehicle, that collector will not only be in contact, but have some safety factor there. So I would say over the most extreme of loading conditions, that we're covering no more than 2/3 of the available shoe geometry. Excellent question. Thank you. Any other questions? Well, I'd like to thank everyone again for joining us. Again, if you have any other questions, feel free to contact me directly. I'd be happy to provide you, any assistance or information that we can. And also, I'll put a plug in for the International Monorail Association. I'll admit that I hadn't been a member. We didn't join, and I wasn't really sure if it was worth the time and effort. And I've got to tell you, it's a fantastic organization. It's small but growing. I was very impressed with the depth and breadth of the membership, their knowledge. They're willing to share information. So if you're in the monorail business, I would strongly suggest considering joining the IMA. Systems over seawater and operation. We have done applications both with transit and other aluminum stainless steel conductor applications in seaside applications. I mentioned our one customer specifies 316 stainless, and this is when they have seaside environments. The 6000 series aluminum alloy, it's usually a 6101, is considered near marine grade, highly corrosion resistant, has silicon and nickel in it, gives it very good corrosion resistance. So that coupled with a 300 series stainless and a 316, not just for the contact surface but also for the hardware, would be advisable in a seaside operation. We have other conductor systems that are used in ports for powering ship-to-shore container cranes. These are located in a trench. Usually they're medium voltage, up to 15,000 volts. And from time to time, these get dumped with bilge seawater. And these systems are highly reliable, withstanding the regular exposure to seawater over 20, 30, 40-year lifetime. So again, when it comes to longevity, the biggest problem is electrical erosion, that arcing and sparking when the collector makes and breaks contact with the conductors. All right, well, with that, we'll knock it off, and I want to say thank you particularly to the folks that are in a different time zone. I know some of you are up really early or stayed up late to attend. And again, I want to thank the International Monorail Association for giving me this opportunity. Thank you, everyone, and have a good day.